Hey everybody. Today we're going to take a look at using Taylor polynomials to make approximations to functions and to see how the difference between those acts as we get closer or further away from the center of convergence. So we're going to need our calculator member for the first thing here. There is a practice packet that I have that goes with this. If you don't have it, I have the examples here and you can get the packet here soon. But let's take a look. Sometimes this can be thought of as a challenging topic on the AP exam, but actually it's not as bad as you think. And we'll go through some examples just so you can understand the underlying principles going on here. So 9.3, Taylor's theorem and Lagrange error bound, two things that we're going to discuss here. All right, so let's remember that Taylor's series, we can use them to approximate values of functions like those transcendental functions, sines and natural logs and things like that. So we've memorized a bunch of those. So I would like to take a look at the sine function and its fifth order Taylor polynomial centered at 0, or the Maclaurin series, just out to the fifth order. And so when I go to graph those, if you want to pause me now, go ahead and put the sine function in, and then just put in the fifth order. That means 5 derivatives out. So it's going to be, you see that fifth power term. Go ahead and graph both of those at the same time. And what I want you to do is trace to a particular value of x close to 0 and go back and forth between both of the curves. Well, the difference between those two curves is the error, the actual error. So on the left, I have a picture of the sine function that's in blue, and the polynomial that's in red. You can see that. But what I'm doing is I'm saying, okay, what is x equals 1? What is its value of the sine function? Well, it's 0.841471. And then I toggled up, staying when x equals 1, and saw the polynomial approximation at x equals 1 and 0.8416667. Well, good grief. Took me out to 4 decimal places where I started getting a difference between those. So that's really good approximation, you know, and all I had to do was go out to 3 terms into the Taylor polynomial. Well, the difference between those two numbers would be the actual error. Well, what we're going to be interested in is sometimes we may not be interested in what the actual error is. We might want to figure out, okay, how bad could the error possibly be? What is a maximum that the error between the two functions could be? So the difference between the polynomial approximation and the actual function between those two functions at a particular value, probably staying close to the center of convergence. So we're going to try to maximize that. So let's just kind of take a look at just kind of setting the idea of what error is and how we find error. So on the worksheet, we've got our 1 over 1 minus x function. That's our geometric series. I want to use that to approximate f of 0.1 using the second degree Taylor polynomial. Now we're going to be doing this at x equals 0 with my center. And I want to then find the error. So given my function, let's use a second degree Taylor polynomial to approximate f of 0.1 and find the error. So let's find the value of the function at 0.1. That would be like finding the sine function in the last example. Well, it comes out to be 1.1, repeat. And now I want to take my polynomial of degree 2. Well, this is just the geometric series with terms 1 plus x squared plus x cubed and so on and so forth. So substituting 0.1 into that gives me 1.11. So the error is simply the difference between the two. So going just 1/10 away from the center of convergence, which is at 0, I am getting a really good approximation. The difference between those two numbers is, you know, going to be just a little bit above 1/100th, 1/1000th, I should say. So really good approximation. Does a really good job with it for a value that close. So how about this one? So what about the error for the 4th degree polynomial approximation of cosine when x is equal to pi over 4? If you want to pause me here, see if you can do the same thing of what we just did in the last problem. Okay, so let's find the value of the function at pi over 4, which we can. So cosine of pi over 4 is 1 over the square root of 2, or 0.707. Here's my 4th degree polynomial for the cosine function. I turned the 2 factorial and the 4 factorial into their actual values there. And so let's approximate then the error, or actually find the error, by taking the difference between the cosine function at pi over 4 and the polynomial function at pi over 4. And notice I'm using absolute values because sometimes it might be less than the actual value, and sometimes it might be greater. And error has no direction. We don't care if it's positive or negative. So the difference between those two is really, really small. So the cosine function does a really good job at approximating even with small numbers of terms in the polynomial. That's incredibly close. And pi over 4, that's around like a quarter of a way, 0.75. So really good approximation. Okay, so here we've been able to actually calculate what the actual error, but we want to see if we can find a maximum of the error without having to go through this process. So this is what we're going to get into here. When we use a part of the Taylor series to estimate the value of the function, we're chopping off a whole infinite number of terms through the rest of the polynomial. In the last one, we went up to a degree 4, but then all of the terms from degree 6 and greater, they got chopped off, and that's what's known as the remainder. And if we know the size of the remainder, we can then give a good idea about how good our estimate is when we're doing our approximations. So let's take a look at one more example on the worksheet here for a geometric easy. This is pretty series, this is easy. So let's say we're using this geometric series, 1 over 1 minus x squared, and we're going to use those first 4 terms, or a 6th degree polynomial approximation. And we're going to do that to approximate between -1 and 1, the interval of convergence for that geometric series. Well, the part that I chopped off, or that I truncated, was everything with the 8th power of 8 all the way up to the infinite powers. That's called the truncation, or the truncation error. And the truncation error itself is another polynomial, or that can be, it's a polynomial that is a geometric series. First term is x to the 8th, multiplied by 1 over 1 minus x squared. So when I'm truncating, I'm dropping off all of those other terms. So that's an idea in terms of the polynomial. That's what we mean by the truncation error, or what Taylor is going to call the remainder. So here's Taylor's theorem for the remainder. And he says, if a function has derivatives of all orders on an open interval, so all orders meaning all the derivatives, then for each positive integer n and for each value of x on that interval, well, I can take my first couple terms. Here's my first term on my Taylor polynomial. My second term with the first derivative, first power over first factorial, second, and so on and so forth, all the way up to the nth. Either we'll decide or the question will decide what the n value is. Well, all the terms beyond that that got chopped off, that's my remainder polynomial of order n. So that's what he's calling the remainder theorem. All those terms that got chopped off were n. Well, what Lagrange had said, well, we can maximize what that error is going to be with this expression. And if you look really carefully, this remainder, which is all those terms that got chopped off, is equal to, or will be maximized, I should say, by the nth plus 1 derivative. Notice we ended with the nth derivative. So if I go one more derivative away, I'm going to take the nth derivative at some value c, I'll talk about that in a second, over n plus 1 factorial, x minus a to the n plus 1. So basically, we're just going to the next term that would appear. Because remember, all the terms after that should be getting smaller and smaller and smaller at whatever my approximated value is. So I know that the maximum error is going to happen at this particular the next term in this series. Well, there is a value of c somewhere between a, my center of convergence, and my value of where I'm trying to do my approximation at, which is going to be x. So a is where my center of my interval of convergence is. X is where I'm trying to do my approximation at. We did recent one at pi over 4 and another one at 0.1. Well, between those two values, the derivative, the nth plus 1 derivative will be maximized. Now, typically, I will tell you, it usually typically happens at the point where we're trying to find the approximation. So whatever that value of c is, that's going to maximize the derivative. That's what I'm going to want to find my derivative value at. Sounds complicated, but it's actually not, and I'll show you. So that, again, that C value is somewhere between the center of the interval of convergence and my X value where I'm doing my approximation. If I can calculate this value, then I will calculate the maximum that the error could possibly be. Now, what we will wind up seeing is that sometimes this is actually a really, sometimes an overestimate of what the error should be. We can maybe sometimes tighten it up a little bit, but at least it's giving us some kind of a range of what the error could possibly be, the maximum error, the difference between the polynomial and my actual function at the value I'm trying to approximate at. Just think about toggling back and forth between those two functions. So a couple things to make note here. This is called the remainder of order n, or the error term. Looks like, again, a lot like the nth term, n plus 1th term in the series. It's next, right after, so if I'm doing a 5th order Taylor polynomial, I'm going to go to the 6th. N plus 1 term will be the 6th power, 6 factorial, and the 6th derivative. I'll show you examples of that. So we'll it seems kind of vague, but let's get in there and take a look at this. We're going to be putting this on our foldable. So make sure you're getting that on your foldable. All right, so let's say we're dealing with the sine function centered at 0. So our basic sine Maclaurin series. And then there exists a value of C between x and 0, such that on my interval from 0 to 0.2, well, let's see what happens here. Here's my sine function. So the first couple terms, and I'm going to go out to the 5th term, and then this next, or sorry, the 5th degree, and then I'm going to go to the 6th. This will represent that next term in that series. Well, in this is going to be the 6th derivative at C. Well, the 6th derivative of sine, if you go through the sine function, go through its derivatives, that's going to be negative sine. Well, I've already got a subtraction here, so negative, the 6th derivative is going to be negative sine. That's why it turns into plus. So here's the sine function approximated at 0.2. So what we're going to say is that on the interval from 0 to 0.2, the largest that the sine function's derivative can be anything between the sine of 0 and the sine of 0.2. Well, clearly the sine of 0.2 is going to be bigger than the sine of 0. So that is my biggest that the derivative is going to be. So let's put this into the Lagrange error. So there is my biggest derivative for the 6th derivative, because we were just doing our approximation at 5th degree. So there's the maximum of the 6th derivative, which was at 0.2, over 6 factorial. And then at 0.2, which technically this would be 0.2 minus 0, because my center was at 0, to the 6th power. And so we will wind up seeing, and this is incredibly small, that the maximum of my error could be is this value. I know that doesn't put it into too much context, so maybe let's look at this and actually see what the actual error was. So the sine function at 0.2 minus the polynomial's approximation at 0.2. This is literally like us toggling back and forth between our functions at the very beginning. Well, turns out to be 2.54 times 10 to the negative 9th. And that number, hopefully you can see, is actually less than what the maximum error that it could possibly be. That was my maximum error bound. So the actual error came underneath of my maximum error estimate. So it worked out. Things worked out okay and gave us a good estimate of how bad our error could be. So let's look at another example here. So let's see what's happening here. If we're trying to do a trying to perform a 2nd degree Taylor polynomial approximation of 1 over 1 minus x. So here's our nice geometric series again. I'm going to go to the 2nd degree, which means I got to go to the 3rd derivative. So I got to go to the nth plus 1 derivative. So I'm going to take 3 derivatives here. There's my 3rd derivative coming out here. So, and it hasn't been mentioned yet, but we're going to do our approximation at 0.1. We're centered at 0. And we're going to then see, okay, what's the maximum that this 3rd derivative could possibly be? So the 3rd derivative at 0 is 6. The 3rd derivative at 0.1 is 9.145. So that's a bigger value. So that's the biggest that my 3rd derivative could possibly be. So putting that then into Lagrange formula, here's my biggest derivative for the third term, or third derivative, I should say. Here is x minus a, or 0.1 minus 0 to the third over 3 factorial. Again, I was only going out to the second degree, so this is all focused on that next term in the series. So the biggest that my error could be is 0.00152. Well, let's put that into context. Let's see how that worked out. So let's calculate the actual error. All right, so the value of the function, 1 over 1 minus 0.1, so that's just me going back into the function, is 10/9. Putting 0.1 into the polynomial, okay, so the second degree Taylor polynomial for this geometric series, this is geometric series 1 plus x squared. Well, putting that into there, I get 111 over 100. So what was the actual error? Well, the difference between those two numbers is 0.001111. But my maximum error was 0.00152. So therefore, the actual error came less than what was predicted to be the maximum that the possible error could be, approximating 1 over 1 minus x with a second degree Taylor polynomial at 0.1. So hopefully that's kind of putting into context how this formula is working. So let's do another one. So I want to find a third degree Taylor polynomial approximation for e to the x at 1, centered at 0. And then I want to find a range of possible values for e to the x at 1, centered at 0. So to find a range of possible values, we're going to have to use that Lagrange error bound. So we're going to find that value, approximate that value at 1, and then use the error bound to say, okay, my error could be this much above or this much below the polynomial approximation at 1. So let's see what we're doing here. So here's my e to the x nth term. This is my nice easiest one. So here's the polynomial written out to the third degree. So 2 factorial and 3 factorial are in the denominators. And the polynomial approximation at 1 is 8/3. So e to the x approximated with the third degree Taylor polynomial has a value of 1, approximate value of 1 at 8/3. So now what I want to do is try to find the maximum error. So now I'm going to go out to the fourth derivative. So the fourth derivative, and 0 minus 1 to the fourth power over 4 factorial. So this is x minus a to the fourth. This is 4 to the 4 factorial. So I got to figure out the fourth derivative's maximum value. Well, e to the x's fourth derivative is e to the x. And I'm centered at 0 and I'm approximating at 1. So I'm trying to figure out, okay, what's the maximum that the derivative could be? Well, e to the 0, I'm going somewhere between 0 and 1. So this is, don't get thrown off, this is the letter Z, but earlier we called these C's. I'll just change this quick so it matches my formula. So this should be a C and this should be a C. All right, so now fourth derivative at 0 is going to be 1, but the fourth derivative at 1 is going to be e. So e is a bigger value for my derivative on this interval. So there is my maximum error. My maximum error is e over 24, or 0.113. So what I want to do now is create a range of possible values. So my polynomial approximation was 8/3. So therefore, I could be e over 24 above that or e over 24 below that, and putting that into some numerical values that turns out to be that range. So my value for e to the x at 1 could be anywhere between those two values. So let's see how this worked out. So the actual value of e at 1, obviously, is 2.718. My approximated value, this is what I did earlier, was 8/3, and this is me now showing, substituting all of those in. So it was 2.666. So 2.666 is actually the center of that range of values. It's literally the midpoint of those values. And my actual error itself, the difference between e and negative or minus 0.83, came out to be 0.052, and that was less than the predicted maximum error. So hopefully that's kind of putting a picture with our Lagrange error bound and how we can use that to do some approximations and create some ranges. All right, let's do one more here. So 4th degree Maclaurin polynomial approximation for cosine at a equals 0 evaluated at 1. Find the Lagrange error bound. So maybe go ahead and pause me here and see if you can try this problem based upon what we've just done. So here's my nth term of my cosine series and the first couple terms of it, getting out to my 4th degree as was asked. And the 4th degree Maclaurin polynomial, I just realized I spelled Maclaurin awful. So the Maclaurin polynomial at 1 is 37 over 24. So that's what the Maclaurin polynomial says the cosine of 1 is if I'm only going out to a 4th degree polynomial. So now I'm going to do my approximation here. Now with trig functions, it's a little tricky because the trig functions, if I go to the next term, the nth plus 1 term, so I'm going to go to the nth plus 1 term here. So I can either look at this as substituting n plus 1 in for n, but if you think about it, substituting n plus 1 in for n, it winds up actually skipping to the next even polynomial derivative. So here's that nth plus 1's derivative, which in this case is going to be 6. So let's see what's the biggest. So the 6th derivative of cosine, well, the maximum that's going to be anywhere between 0 and 1 is going to be 1. Maximum that the cosine could be is going to be 1. So I have 1 is my maximum of the cosine function. Set it at 0, so it's 1 minus 0 to the 6th power over 6 factorial. So it's going to the next non-zero term in my polynomial, which again, if I were to do the 5th derivative, that would be getting me a sine function, and that would give me a 0 for that derivative. So we go to the 6 for trig functions. So 1 over 720, that's my maximum error, which comes out to be this small decimal value. So again, let's put this into some perspective. By the way, that's the answer. That's my Lagrange error bound. But my actual value of the cosine at 1 is 0.5403. The polynomial approximated at 1, so it's just me putting 1 into the equation here, is 37 over 24, which is 0.5417. So the actual error, and I should be really getting into a habit of putting absolute values around these, just in case they come out to be negative. So the actual error is 0.0013643, but my estimated maximum error was 0.001388. So therefore it comes in less than that. So my actual error came within the error bound, the maximum predicted error at 1. All right, there's one more example in the packet to do, and maybe we'll do this in class. But what this is a little bit kind of backwards is we're saying, okay, I'd like to approximate the cosine function, but I want to make sure I have enough of polynomial terms so that the error comes out. This is my calculation for error, the difference between the polynomial and the actual function. I want the error to be less than 0.001. So what we can do is we can do this graphically. I can graph the cosine function in y1, and then I can start graphing polynomial terms in y sub 2. And notice that I'm going to be on the interval from -pi to pi. So what I would want to do is to go in my graph and toggle back and forth between the polynomial and the cosine at pi and see if the difference between those two is less than 0.001. In fact, you might want to even make a third term, or sorry, a third graph. And what I would suggest is you can make a third graph, turn off the first and second graphs, and make a third graph that's just graphing the absolute value of the difference between those two. And then systematically go into y sub 2 and keep adding additional terms. And you're waiting to see when this graph dips below a constant function or a value of 0.001. So it's a little bit of trial and error until you get that to work out. All right, so it's a lot to kind of handle here. So we'll talk about this over the next couple of days. Typically, I'll tell you there's at most one multiple choice problem. and maybe one free response question on this. So let's not sweat it too much.